Today we're going to introduce the Danzig simplex algorithm. First of all, I'll give a short introduction. The simplex algorithm was invented by George Danzig in 1947. The simplex method is the earliest solution algorithm for solving linear problems. It is an efficient implementation of solving a series of systems of linear equations. By using a greedy strategy while jumping from a feasible vertex of the next adjacent vertex, the algorithm terminates at an optimal solution. To learn the algorithm, the first thing we need to know is the standard form. Here is the definition for standard form, and there are a few conditions to make it a standard form. First of all, the objective function, which is this one, must be a maximization. If it's not a maximization, which is in this example, then we have to multiply this by -1. Then we get the maximization. Secondly, the variables must have a non-negativity constraint. If one of them have negativity constraint or doesn't have a constraint, which like y in here have no constraint, so we have to convert y to y1 minus y2. And then we put the constraint for y1 and y2 in the end. They must be bigger or equal than 0. And moreover, if the inequality sign is not the one we want, like for example, here we have the bigger or equal than sign, so we have to multiply both sides by -1. Then we got the right sign for this. And of course, if we have a equality sign, then we have to change it to inequality signs, and the number of equations becomes 2. After transforming to standard form, we move to the next step, slack form. In the given definition, we can see that Z stands for the equality version of objective function, and xn plus I are the new variables, slack variables. They are supposed to be non-negative, since the simplex algorithm requires them to be positive or 0. For now, I'll let my partner to introduce a few more examples and the details about how to transform to slack form.
For now, we will talk about slack form. As you can see, this is standard form. All variables have non-negative, but for simplex algorithm, we need to convert standard form into slack form. To do this, we need to introduce slack variables. In this case, x4, x5, x6. We add all these variables, and these x4, x5, x6 are also larger than 0. And then we need to change our objective function by rewriting the inequality. Now we are good to build our simplex table. We put all the coefficients in the top of the table and objective function at the bottom. So these are from the changed standard form with slack variables. So now we have simplex table. By simplex algorithm, we need to find largest negative number from objective function for our entry, and this would be our pivot column, since the -6 is the largest negative, and we set these column with -6 as pivot column. With this pivot column, we can find the smallest ratio by dividing the constant of each row with the pivot column element. Since the 90 is our smallest, we have pivot row and pivot column. Since we need to make the pivot column to 1, we have to divide this by 2. We have new pivot row, and we have to make these rows to 0 by row operations. We could achieve this by these operations. Now we have new simplex table, and we have to repeat these process until bottom row, which for objective function doesn't have negative number. As bottom row isn't optimal yet, we need to do more iterations. Largest number in the objective function, our pivot row and pivot column, and our new pivot row. With the row operations, we now have new pivot rows, and we are done since there is no negative number at the bottom. Column of x1, x2, x6, and z are basic column since there are unique column. Therefore, x1 equals 48, x2 equals 84, x6 equals 60, z equals 708. But column of x3, x4, x5 are non-basic, so they are all equals 0. So our max would be 708.
After the calculations, we need to discuss the time complexity. In 1972, Klee and Minty proved that the worst-case complexity of the simplex method by Danzig is exponential time, because in the worst case, the simplex algorithm indeed visits all to the power of n vertices, and the complexity will be big O to the power n. It is an open question if there is a variation with polynomial time, or even sub-exponential time worst-case complexity. And this is the end of our lesson. Thank you.